Welcome to qnawire.
In problem 127, we're asked to find the centroid of this area that is rotated around point H. And we can start off by finding the centroid in the x direction, because it's simply equal to the point H, which is the point of revolution, so it'll be equal side of volume on either side of the x-axis. It'll be symmetrical in that way. And then we can also find the centroid in the z direction, which will be 0 because it's revolved around point H, so there's equal sides on the xz plane of volume. And so we're left just needing to find the centroid in the y direction. And we'll use this equation to find it, where the centroid in the y direction times the total volume is equal to the integral of the differential element centroid. And that differential element will be a disk shown here in green that is integrated throughout the volume of the object along the y-axis, or parallel to the y-axis. So first let's find the volume we'll need for this equation, which is equal to the integral of that differential volume. And the differential volume is going to be equal to the area of a circle, pi r squared, times dy, to get that differential disk at each point along this object parallel to the y-axis. Now we don't know the value of r, so we'll have to find that. And when you do that, we can use the equation of the line they gave us. And since the radius goes along the x-axis, we can actually plug in the radius for x in that equation. So now it's r squared over h squared plus y squared over a squared is equal to 1. And solving for the radius, we get that it is equal to h minus h over a times the square root of a squared minus y squared. And now we can plug this back into our differential volume. Now we can plug that back into our equation for volume and take the integral from 0 to a to get the total length of this object. Now to solve this integral, we're going to have to convert y in terms of a and sine to make it possible. So y is also equal to a times the sine of theta, Therefore, dy is equal to a cosine theta d theta and now the integral is going from 0 to pi over 2. And we can plug in for y, plug in a sine theta for y. And then we can also plug in for dy, a cosine theta d theta. So simplifying this to a point that we can integrate it, get a squared minus 2a cosine theta plus a squared minus a squared sine theta sine squared theta and we have our dy at the end. And we can simplify this even further. By multiplying the a cosine theta through. Now actually solving the integral, we get pi ah squared times 2 sine theta minus 2 theta over 2 plus sine theta over 4, well, 2 theta over 4, minus 1/3 sine cubed theta, and this is all from 0 to pi over 2. And plugging in those values, we get that the volume is equal to 0.09587 pi a times h squared. Now the only other part we'll need for the equation is the integral of the differential element. This will also go from 0 to a. The differential element in the y direction will just be y. I mean, the centroid of the differential element will be y, because it'll be along a point y as it goes parallel to the y-axis throughout the volume. And we solved for dv earlier, so we can just plug dv in. And the only difference here is the additional multiplication of y to this integral from the integral before. And that will actually help us so we don't have to use the sine and cosine values to simplify the integral. So multiplying everything through, we get this. And this we can solve. So solving the integral, you get this from 0 to a, and then plugging in 0 and a, we find that the integral of the differential, the centroid's differential element, dv, is equal to 1/12 pi a squared h squared. Now we know enough to solve our original equation. So we plug in the volume we found, the 0.09587 pi ah squared on the left side, and then we can plug in the differential element on the right side. And solving for the centroid in the y direction,